Pilot might black out under heavy G-forces, but the absolute limits of flight are dictated strictly by mechanical physics and aerodynamics. Predicting catastrophic failure requires translating invisible aerodynamic forces and material stress into a precise, mathematically bounded operational envelope. We measure this stress using load factor. Plotting this requirement creates an upward curving line. This forms the positive stall boundary. We plot a mirroring, downward curving line below the axis for negative flight maneuvers. Aerodynamic stall is not tied to a single static speed. It is a dynamic wall that shifts aggressively as load factor increases. With the aerodynamic walls in place, we move to the rigid upper and lower material limits of the graph. We plot these operational stress maximums as strict horizontal lines. Between these lines, internal structures flex elastically and return to their original shape. For a massive safety margin, the ultimate load factor is plotted further out, typically 1.5 times the limit load. Look at the precise point where the upward stall curve intersects the positive limit load line. This coordinate is corner speed. Operating exactly at corner speed yields the tightest possible turn radius and the absolute maximum tactical maneuverability the machine can physically provide. This completed chart shows the full mathematical model, mapping all aerodynamic and structural limits into a single visual. This highlighted interior region constitutes the aircraft's absolute safe flight envelope for all maneuvers. There is one final limitation closing the box on the far right: the terminal never exceed speed. Crossing this extreme high-speed boundary risks aerodynamic flutter and structural resonance. The VN diagram is the ultimate mandate. Operate inside the envelope and the aircraft performs. Cross the lines, and physics takes over.